Hello everybody, welcome to a video about section 12.1. Let me again apologize for having to cover the material this way. I realize this is not optimal, but the day we're supposed to cover this material, I'm at the hospital with my wife. So this is the best we can do given the circumstances. We just cannot lose 2 days of material. So I appreciate you following along with the material this way. This first section is an introduction to three-space. So just to motivate what we're going to do, I want to introduce that place to you and then talk about how you graph there and then give some equations of specific objects there, in particular a sphere. So basically the way this material goes is we think about what it meant to graph in the XY plane, and then we're going to sort of cantilever that up into an extra dimension. So the XY plane is two-dimensional. We're now going to move on to 3 dimensions. That's what three-space is. Okay, so just a reminder, what is two-space? Two-space is a fancy way of talking about the XY plane, also denoted r squared with this fancy sort of capital R there. And to locate points there, as I'm sure you know, you need to specify 2 numbers. And the corresponding point is just AB, and the numbers form a little rectangle. So here's 1, 2, 3 on the x-axis and 2 on the y-axis. You make this little rectangle, right? So when somebody says to you, go to the point 3, 2, then you do what you've been doing since 6th grade or whatever, you know. You march 3 units in the positive direction on the x-axis, then 2 units in the positive direction on the y-axis. With negative 1, 4, you move 1 unit in the negative direction on the x-axis and then 4 in the positive direction on the y-axis. So anyway, two-space is two-dimensional because to tell me where you are, you must tell me 2 pieces of information, an x-coordinate and a y-coordinate in this case. Well, three-space is similar, it's just that you need now 3 pieces of information to specify where you are, and there's a third axis. So here are my x and y axes like before. Now there's a vertical z-axis. Points in three-space now have 3 coordinates, the familiar x and y coordinates plus a third coordinate. Now what is initially sort of confusing about the way we draw three-space is that if you think about drawing the xy plane, which I don't have, well, here, right? XY plane. If it's drawn on the board or on a sheet of paper, it's sort of vertically oriented, you know, like a board in our classroom is a vertical wall, you know. The way that we draw the XYZ three-space, the XY plane is still there, but it's on the floor. Okay, it's not on a wall. If you want to think about what the wall is now, it's this YZ plane, right? If you draw out the points there, that's what's sitting on the whiteboard now, and the XY plane is on the floor. The XZ plane is sort of coming out of the whiteboard at you. So we have to sort of shift our perspective some. We're not used to thinking of the XY plane as being on the floor. We're used to thinking of it as like being on a wall. You have to sort of shift your perspective now. But anyway, now in three-space, this point, to get there, you just walk A units on the x-axis in the appropriate direction, you know. So if it's a negative A, you'd walk backwards. B units in the y direction, so this is showing you that path, right? A, B in the y direction, right? You're walking parallel to the y-axis. And then that C gives you some height. So you walk either up or down, depending on if C is positive or negative. And now, this point determines a box instead of a rectangle. So, you know, a box is a 3-dimensional version of the 2-dimensional rectangle we had before. So that's three-space. That's how you specify points there. Here's some examples of points. Here's the point, negative 4, 3, negative 5. The way you find that point is you walk 4 units in the negative direction on the x, 3 units in the positive direction parallel to the y-axis, and then 5 units down. So in the z-axis direction. This point here is 3, negative 2, negative 6. 3 steps in the x direction, positive now. 2 steps in the negative y direction, parallel to the y-axis but backwards, and still down. And there's that point. Okay, so that's how you plot points in three-space. So here's just a little picture of what's happening. The XY plane, as I said before, is a floor. The YZ plane, again, is kind of like the whiteboard. The x-axis is kind of coming straight out at you from the board, you know. So the XZ plane forms this sort of green thing coming out at you. That's what's giving it 3 dimensions there. Okay, so another reminder, how do you graph in 2-space? Well, in 2-space, the graph of an equation gives you a curve. This is something you are all intimately familiar with, I think, after having finished 2 calculus classes. And just recall, a point AB is on the graph if and only if, when you substitute A for X and B for Y, you get a true statement. So here's an equation involving X's and Y's. Notice the point -1, 0, or sorry, excuse me, I said it backwards. 0, -1 is on the graph. And why is that? Because if you substitute 0 for X and -1 for Y, you get something true. On the other hand, 0, 2 is of course not on the graph. So this is all familiar to you, right? But we're going to take this idea now, move it up into 3-space in a second. The key idea is the substitution thing, right? You're thinking about, is this point on the graph or not? And the answer is yes, if and only if when you do some sort of substitution, you get a true statement. So here's the unit circle, right? So these graphs don't have to be functions, by the way, right? This guy here is a function, this guy is not. So just for emphasis here, let me graph something for you. These equations that I was looking at here, this x squared minus 1 and whatever, these are pretty tame. You can, of course, have wacky equations. So I'm going to graph sine of xy plus log of y equals 4 or something. I don't know, just whatever. Produce nothing. Okay. Yeah, there you go. Okay. So that produced something with a 1 there. Let me move this around a little bit. So, you know, that's a curve, or I guess a series of curves, right? Every single point on these curves satisfies the fact, right? Satisfies the property that sine of the x value times the y value plus log of the y value is 1. That's how a point gets to be drawn here, right? So this point right here, whatever this is, what, -1, 1, must not have that property. But, oh, -1, 3, I guess, has that property somehow, right? So anyway, the equations don't have to be nice, right? Any equation, any random thing you write down has a graph, unless you contradict yourself or something, right? So you can have graphs that don't show up if you aren't careful. But anyway, that's how graphing worked in 2-space. Okay, graphing in 3-space works similarly. Now it's just your equation involves x's, y's, and z's, and a point is on the graph if and only if the corresponding substitutions work now. Okay, so let's consider this equation or statement, z equals 3. What kind of points live on the graph of that equation? So now you have to think about points with 3 coordinates, a, b, and c, so that when you make the corresponding substitutions, you get something true. So here's a point, 1, 4, 3. Is that a point on this guy's graph? Well, notice the x and y's are kind of irrelevant, you know. There's no x in this equation, there's no y in this equation. So really all you're asking yourself is that third coordinate 3 or not. And in this case the answer is yes, you know. So that point is on there. This one though, notice is not on there. Z is not 3. This point is on there, you know, and so on. So you pretty quickly realize that, oh, to be a point on this guy's graph, all you need is for the third coordinate to be 3 and nothing else matters. So here's what those points look like. If you want to see what the graph looks like, it looks like this. So just all points whose third coordinate is 3. This is a picture from your text. Let me go to the GeoGebra calculator. This is the link from your syllabus that graphs in 3D. So I'm going to tell it z equals 3. And notice what it graphs. It graphs a plane now, not a curve, but a plane. So notice the dimensions have increased, right? Our graphs used to be one-dimensional. They used to be curves. And now we get graphs that are surfaces, okay? So now, yeah, you can see from the side, right, that is z equals 3. If I tilt, you can sort of see it a little better, right? So anything like that, right? Z equals 3, Z equals 2, whatever, right? It's just the corresponding flat plane there. Okay, where the x's and y's don't matter. All that matters is that z coordinate is whatever you tell it to be. Okay, so let's just play around with some more graphs. That was z equals 3. Y equals 5. What kind of points live on the graph there, right? And again, you could think about different points, but you come to the same kind of conclusion. Now the y coordinate is all that matters. So the x coordinate can be whatever, because you can't really substitute it, right? Z coordinate can be whatever. Here is y equals 5. All that matters is the y coordinates are 5. So let me come back here and just sort of spin it around a little bit. Y equals 5. Okay, so on this, oh, it doesn't extend far enough. Here, let me zoom out. Well, I thought that zoomed out. Well, whatever. Zoom back in. Whoa. Okay. I'm just going to bail and come back. Let me just do y equals 1 to be a little more careful. Okay, so in this calculator, the green axis is the y-axis, and notice there you go, right? Y is 1. You just get that flat surface there, that plane. Okay, so let's come back now. Here's kind of a harder one to think about. X squared plus y squared equals 1. And the reason that's a little hard to think about is simply because, I mean, you guys already know what that is, right? Because we did it. Where is it? Way back here. Sorry. Right here. Here's x squared plus y squared equals 1. It's a circle. You know, it's the unit circle. So on one hand, it's sort of silly to ask you what the graph of this looks like. But now we're graphing in 3 space, you know? So there actually are z coordinates here. So the question is, if you graph this equation in 3 space, do you get the same thing, just a circle in the xy plane? And the answer is no. So let's just think about what it might look like. Here are some points. Let's think about if they live on this graph or not. Okay, 1, 1, 2. 1 squared plus 1 squared, and now the z, there's nothing to substitute, right? So it doesn't matter. 1 squared plus 1 squared is not 1. So this point right here is a no. 1 squared plus 0 squared equals 1, though, right? And the 4, again, doesn't come into play. 1 over root 2 squared is a half. 1 over root 2 squared is a half. Half plus half is 1. And again, the 2 doesn't matter. Okay, so what kind of points live on this? A, B, C, so that a squared plus b squared is 1, but there's no restriction on that third coordinate, you know? So let's think about what that looks like. Come back here. X to the second plus y to the second equals 1. Notice, if you look at it from above, okay, which I can barely get it to go there, right? Look at it from above, that little blue, right? That's the unit circle in the xy plane. But now, there's no restriction on z. Your height can be anything. So you basically take that unit circle and give it height. And now you get not the curve that the unit circle was, you get a cylinder. You get something two-dimensional. This is a hollow cylinder that stretches infinitely up and down. Okay? So again, just to emphasize here that graphing in 3D is similar to graphing in 2D, let me just open a new... I'm going to do a 3D graph on my graphing app on my machine. This is a Mac-specific application here. The GeoGebra thing can't handle wackiness sometimes. So let me just do like, I don't know, same kind of thing I did before. Sine of x, y, plus maybe like log of xz, xz equals 1. Right, that's kind of a wacky equation, but it's an equation involving x, y, and z. Let's hit enter here and see. Okay, that's the surface you get. Okay? It's crazy. But again, the way that these points, these green things here at the surface, the way you get to be on that surface is sine of your x times y coordinates plus log of your x times z coordinate is 1. You know? Okay. So you get this cylinder here. Okay, so I want to end this first part of the video here just to break this up a little bit. So when we come back, I have maybe like 5 or 10 more minutes of graphing things to look at, and then we'll be done with section 12.1.